Hi, my name is Igor Arsovski. I'm the CTO of the ASIC business unit at Marvell, and it's my great pleasure to be with you at the AI Hardware Summit today, even if it's virtually only. Today, I plan to take you through Marvell's custom silicon capability. The first portion of this presentation will focus on the ASIC, the Marvell ASIC team that is leveraging differentiated IP, methodology, and advanced packaging to enable the next generation of AI systems. It is my great pleasure to also announce our partnership with Grok, where we have helped enable the first peta-op accelerator in the industry. The second portion of this presentation will focus on embedded AI and how we're leveraging the most complete data infrastructure portfolio to enable custom silicon in the data center space and the automotive space. But before we dive into the meat of this presentation, let's take a look at some industry trends and how they've affected custom silicon. In the quest for power, performance, and cost optimization, a number of companies have switched from standard products like GPUs, CPUs, and FPGAs into more custom silicon like ASICs and domain-specific accelerators. Google started with the TPU, Amazon introduced Inferentia, Baidu, Alibaba, and Huawei are all doing their own training and inference devices, and Tesla is multiple generations in on their custom silicon for autopilot. All of these efforts required pretty seasoned silicon design teams, and they all require extreme focus on quality and reliability. As the AI models grow in complexity, we're also seeing this shift to custom silicon accelerate. If you look at the chart on the left, you'll see the AI model growth in a single Moore's Law generation of about 18 months. And what you notice here is that the models have grown by 50x. To achieve the same type of scaling in transistors per die, the silicon semiconductor industry required more than 120 months or 10 years. So the gap is large, the growth gap is large, and it's continuing to widen. If you look at Moore's Law, we are seeing a significant slowdown. And if you look at one of the components of AI accelerators, such as SRAM, we're seeing this gap even widening. If you look at the current scaling of SRAM, it would take more than 4 to 5 years to double the density of SRAM. So this is a significant problem. So let's see what we can do in current best of breed or latest generation of silicon. So if you look at 5 nanometer die, you will notice that you can place about 2 gigabytes of SRAM on chip and access it at the cost of 10 to 50 femtojoules per bit, the energy cost. You can also move a lot of bandwidth on chip, about 100 terabits per second per millimeter. So if you can implement an accelerator on die, this is great. It's going to be very efficient and a very high performance. But in most cases, we find that this is not enough memory, and a lot of companies are moving to the next generation of integration, which is really integrating more memory on package. And here I've shown a die with 2 HBMs, but you can pack up to 6, maybe 8 HBMs. So you can get an order of magnitude more memory closer to the compute, about 100 gigabytes of memory on package, but you pay a significantly higher cost for energy to access that DRAM, about 2 orders of magnitude higher energy, 4 picojoules per bit. And then the bandwidth to access this memory is also reduced by about 2 orders of magnitude. You're sitting at about a half a terabit per second per millimeter type bandwidth, even with the most advanced interfaces like an HBM. Now this could be extended maybe a little bit better. If you look at best of breed chip-to-chip interfaces, they're sitting at about 2 terabits per second per millimeter edge. But you only have so much edge. We're already pushing reticle size designs, and this bandwidth is not going to increase much more than that. So the natural next step is to move into 3D integration. In this fictional design that I kind of put together, you have 4 stacks of 4 dies each with multiple HBMs integrated on top. I assume that 24 gig HBM. So you can pack about 32 gigabytes of SRAM total. You can pack 400 gigabytes of DRAM on this die. So you can get a lot more memory, which is great. But the best part about this is the fact that you can get it at a much lower energy cost. You're back into the femtojoule per bit range because you're only communicating over hundreds of microns versus centimeters or inches in the HBM case. And then you can communicate with much higher bandwidth. We're looking at about 20 terabits per second per millimeter squared. And you have a lot more millimeter squared than you have millimeter edge. So you can move a lot more bandwidth. And this bandwidth is only improving. As the fabs are kind of trying to tighten these TSV pitches, you might be able to move hundreds of terabits per second per millimeter squared. So this is great. The big challenge as we go forward is really the cost. If you look at here, we're driving with large advanced node dies, and then also we're doing some advanced packaging techniques. So one way to reduce cost is to move down the path of modularity. If you look at modularity, it allows you to leverage a mask set, for example, to design multiple different products. So with a few set of mask set, you might be able to integrate multiple MCMs with different solutions. In the top row here, I show an example of Marvell's modular approach. These are all parts that are shipping in high volume production. And we have some unique IP that allows you to minimize the number of mask sets to achieve these different modular solutions. One way to extend modularity is to create these chiplet libraries. So if you look at the second row, you can actually create processor chiplets, IO chiplets, FPGA chiplet, accelerators, memory chiplets, and you can then integrate these onto different MCMs. And this is really current in the industry, lots of different groups talking about this approach. And then if you have these chiplets, you can argue that then you could take these and extend them into 2.5D and 3D and get modularity that way, where you can stack different number of dies, you can stack different dies on top of these and get very powerful systems with a significantly reduced cost. So lots of discussions about custom silicon. Marvell, to address this space, really acquired an ASIC business unit that originally started at IBM and then quickly transitioned through Global Foundries and Avera Semi before landing at Marvell. It's a really highly experienced design team, 25 years of experience, 14 process nodes, technology nodes, and over 2,000 designs that have been delivered in high reliability applications like enterprise networking, mainframe computers, carrier, aerospace and defense, and so on. This business unit brought with it leading edge IP, especially SerDes and high density memories, design services, and a lot of advanced packaging technologies. So with this integration, Marvell was not only able to push the leading edge technology, we have more engineering team to move into 5 nanometer quickly. We actually have 5 nanometer silicon in the lab today, but we were able to offer best in class IO, highest performance 112 gig long reach and extra short reach cores, looking into the next generation of 224 gig. Also energy efficient parallel IO that are really critical for these modular AI accelerators. And then the core of the chip was bolstered with high bandwidth SRAM, which I'm going to show how we use in the Grok example to get highest bandwidth, lots of capacity on chip. And then all of this was tied up with a lot of advanced packaging pedigree that came from IBM, modular MCMs, 2.5Ds in high volume production for us. 3D is also in high volume production. In fact, we were the first ones to offer logic die integrated under a DRAM stack. This was done in conjunction with the Micron team on the HMC, the hybrid memory cube, which was a serial version of the HBM, if you will. So all these differentiating technologies are then tied in nicely with a flexible ASIC engagement model, starting from turnkey on the very right here, where you can see the customer providing a spec and our team really going through PD, floor planning, DFT insertion, all the way till the point where we deliver a tested, packaged, warranted module for the duration of the product. On the very left side here, you see the opposite, where the customer really wants a hands-on approach on a couple of blocks that they really understand well, and they do their own PD or layout on these blocks, and then we take it off from that. And then at the end, we still provide this full support for reliability and quality and so on. So lots of engagement models, a full spectrum that we support. So finally, a perfect example of this capability is Grok's Allen chip, which is industry's first peta-op AI accelerator. We engaged with Grok early in the process, worked together on architecture, technology, co-optimization, picking the right IP, the right memory cuts, pick the right voltage targets, customize flows and tools wherever we needed to do. And we were able to really squeeze out everything out of the technology node that was offered. Grok brought in their innovative architecture to offer unparalleled performance at very low latency. Their architecture also enabled multi-chip scalability and deterministic execution, which is really critical in markets like the automotive space. And then Marvell brought in their dense SRAM that I mentioned earlier to be able to achieve a significant bit count here, 2.5 gigabits of SRAM on chip. We brought in our high-speed SerDes. We brought in our design team capability to do full turnkey PCIe chip-to-chip subsystems. And then we tied all this nicely with a nice reliability blanket with pre-qualified IP, pre-qualified design flows, custom tests, logic redundancy, ECC on all the memories. And really, we owned reliability of this product till end of life. And best of all, we did this with urgency. Final netlist to tape out for this reticle size, first time right AI accelerators was completed in less than 3 months. So this is really an impressive proof point of Marvell's ASIC capability. Now, we're going to shift gears and go into the embedded AI. And this is really where Marvell is in a unique position to serve the market. We already supply standard and custom product and ASICs in the 5G carrier, enterprise networking, data center, and automotive. With the addition of the Marvell ASIC group, now we can leverage this portfolio of building blocks to enable the next generation of custom silicon. So let's take a deep dive of Marvell, of what Marvell has to offer. We have the most complete data infrastructure portfolio of any semiconductor company. We are not only playing in these businesses, we're leaders in these businesses. You can see that by the comments under each of these components. In the processor space, we're number one in baseband and data plane processors with many different firsts. First ARM-based processor to make the top 500 supercomputer list, the first non-x86 processor to make it to the Microsoft Azure platform, and this is the most widely deployed ARM server processor to date. On the storage side, Marvell is also in a leading position, providing storage technology like ultra-fast read channels, leading-edge transceivers, highly efficient analog designs, and powerful cryptographic engines. In the networking, we're number two, recently launching industry's most complete networking portfolio for borderless enterprise. And security really permeates through all these different markets. Marvell's offers nitrox and liquid security product lines that integrate compression offloads and critical cryptography acceleration for SSL and IPsec. And we do also a lot of embedded EHSMs that can kind of permeate through the data center as well as the automotive market. So let's see how we use this broad portfolio across the different application spaces. So this slide shows some of the building blocks that Marvell offers, along with some examples of custom silicon that we offer in the data center. If you look at the left side, you can see the building blocks such as optimized 112 gig SerDes, HBM implementation, machine learning memory, that are really critical to enable the AI accelerators, like I showed in the Grok example. Beyond that, we bring high-performance custom ARM processors, which are really best of breed. Some of these are yet to be announced processors from the ARM lineup. We couple this with programmable logic, switch, encryption, compression, all kinds of network offload to build smart NICs and other building blocks of the data center. And all of this is nicely tied up with the reliability and uptime typical of an infrastructure company. Now, in the quest to bring compute closer to storage. We also offer a number of building blocks from our storage standard products: NAND media controllers, DSP and LDPC ECC, encryption and data protection. And this is coupled again with very low power efficient ARM processors, programmable logic, a vast offering of different interface protocols like CXL, PCIe, NVMe, NVMe OF. We tied this nicely with firmware and full turnkey enablement. And with it, you can enable custom silicon like computational SSDs, where you can pack AI, ML, and CPU right close to the memory, to the SSD, or you can actually use these in the case of disaggregated memory, to move both electrical or through silicon photonics type connections for the data center. And then beyond the data center, we also work in the automotive space, and we look at the car more and more like a software entity. And we really see three different pillars in this centralized type architecture. We see the compute pillar, the storage pillar, and then the Ethernet, automotive Ethernet, that really connects these two to the rest of the sensors and other connections within the car. And in this space, Marvell has been playing for multiple generations. We are number one in secure PHYs and switches. We're number one in multi-gig type Ethernet connections. And with the addition of the ASIC team, now we can couple our ARM and security leadership together with AI accelerators to enable the compute. And then with the addition of the ASIC business unit, now we can leverage a lot of the storage IP like NVMe and NVMe OF type protocols to enable the third pillar of automotive, which is the automotive storage as well. So we're really one-stop shop for automotive silicon, and this is again coupled with really high reliability and uptime. I keep repeating that message because it's kind of critical, and I think on the next slide I'm going to kind of dive a little bit more in details of how we enable this reliability. So the way we approach reliability is a very holistic and proactive fashion. We start with a deep fab partnership to understand the technology intrinsic failure mechanisms. We then take these lessons and we feed them not into our internal IP, but also third-party IP. We set up very strict and rigorous audits of third-party IP, and we then take this IP and integrate it onto test chips that are then integrated with our chip design methodology. So we're actually now verifying the methodology for integration as well. Image and package is also a key component of this. We build these qualification vehicles that go through HTOL and multiple different screens to really give us not only input on how well the IP does across the entire process space, but also they give us insight into the type of test screens that we need to apply to guarantee reliability for the end of life of these products. In the applications such as our automotive and aerospace, we take this up a notch and we employ enhanced escape prevention methodologies that not only screen good from bad chips on a wafer, but they also look at and screen away good chips that are failing in bad chip neighborhoods, and many, many different escape prevention methodologies. In summary, Marvell offers the most complete data infrastructure portfolio in the industry, offering IP and subsystems that can be used to enable the next generation of custom silicon for data center and automotive. We couple this with ASIC powerhouse that has delivered custom silicon for the past 25 years and has a track record of delivering high reliability ASICs in the mainframe, enterprise, carrier, aerospace, and defense markets. We're already shipping multiple AI accelerators with proven capability to support petaop type ASICs. And we are scaling to advanced technologies. 5 nanometer is not only in the lab today, but we're also going to be shipping samples of products by next year. And to tie it all together, we do this by offering multiple flexible business models to enable the next generation of innovation and next generation of AI products. So I want to thank you for your time. And I want to also point you to a number of AI Summit webpage webinars that our team has done that dive into a lot more detail than I covered today on power optimization, packaging, and design for first time right, that kind of give you a little more meat into some of the messages that I conveyed today. So thank you very much, and I appreciate your time, and please stay healthy and safe.